Alô, lūdzu atbildiet.
Jā,
Tā,
mēs
kaut
dzirdam.
kas nedarbojas. Tā, tūlīt tas. Alô, lūdzu atbildiet.
Jūs dzirdat?
Es jūtu vājus dzirdinājumus. Tagad lūdzu.
Un tagad?
Alô.
Halo?
Tā, kaut kas man nedarbojas kā vajag. Tā, es pārstartēšu, ja MS Teams. I'm going to restart MS Teams doesn't work right. Allo, ka tagad dzirdam. Lūdzu atbildiet. Allo.
Jā, mēs dzirdam ļoti labi.
Dzirdam, nu labi. Tagad es arī dzirdēju. Tā. Ekrānu redzam? Allo.
Nē. Tagad jā.
Jā.
Redzam, jā? Labi.
Jā.
Okay. So we became stopped somewhere here, trying to understand what is the reason of different cells, the rods and the cones. So light travels from this side through this layer that doesn't have the reflection or the reflection properties from inside. For instance, light is traveling here through this layer, and after that excites the cells, and the light can't be reflected back from this layer. So that is why if some part of light is passing back, so can't be reflected again to excite the cells. So now we'll go to speak. So we've started to speak about these two cells, and we said that the cells are responsible for the vision and for the colors too. So that is why when the illumination isn't so bright in the twilight conditions, so we don't see the colors. So this means that there are cells that are responsible only to get the image, and there are cells that are responsible for the colors. So these cells, the rod 1, are responsible for the colors, and the rod are responsible for the white-black image, and the cones are responsible for the colors. So this is the scheme of the cell system. The cones, so we have spoken that they have just 3 type of cells that react or detect the blue light, the green light, and the red light. And we stop it at this point. And the next one is to understand how can we get different lights. So this is the spectrum of the cell sensitivity. This is the wavelength. So this is the wavelength, and this is the intensity. So this is the line, the diagram that corresponds to the red, because this one is very close to the red band. So this one characterizes the green light sensitivity, and this one the blue one. So just to give you the sense, as the temperature of the humans 36.6, The wavelength that corresponds to this radiation is 9,000 nanometers, so somewhere 10 times on the right against this digit approximately. So that is why our cells are not able to detect this radiation, and this is very deep infrared radiation. So because of the colors, we can compare the colors with the temperature. And really, if you get, for instance, a piece of metal and provide heat to this piece, the temperature increases and the color of this metal also is changed. For instance, this is a diagram that characterizes the colors and the temperature in Kelvin degree. Have a look here. At the red one, we have approximately 1000 Kelvin degree, and somewhere here at the very blue, the temperature corresponds, this color corresponds to 10,000 Kelvin degree. And now you see you'll see the digital experiment. I pick it up from Wikipedia and have a look. This is the line, the diagram of the spectrum, independence on the temperatures, and here you see the colors. So for the very red, roughly 1000 Kelvin. So let's come back. Okay, so this is the diagram for the red. This is for the blue, somewhere you see 25,000 Kelvin. Okay, very, very blue, so it means very, very high temperature. Is the idea clear to you? Vai tas ir skaidrs, lūdzu, jautājumu?
Ir skaidrs pagaidām.
Lūdzu, atbildiet.
Ir skaidrs.
Okay. So next, because of this, that the colors are connected to the temperature, we can provide different colors, means, and actually from this diagram, from this example, we see that the colors can be changed. When the colors are changed, you see, we have different spectra here. So that is why when we fix, for instance, this color, we can say, oh, we need to select this wavelength, and this wavelength, as an example. So this means the mixture of the wavelengths can give different colors. And for this, we have the diagrams that deliver to us the combination of the colors. Have a look. So for instance, if you combine the red, the green, and the blue, so these are the colors by our cells, RGB standard, the intensity of R of red is A, the intensity of green is B, and intensity of blue is C. And their combination can give different colors. Have a look here. So these are the coefficients Y and X. So Y and X. And for instance, I want to get such a color. What can I do? I'm identifying what is the coordinate for X and what is the coordinate for Y. So here I have approximately 0.55 maybe, and here I have approximately 0.10, 0.28, somewhere like this. So, and if I know X and Y, I know X and Y, and I know that the sum of X, Y, and Z must be equal to 2 units, so this is like 100%, I can calculate now what should be the value of Z. It should be 0.23. So because of this, I know now for R, I need 0.5, for B, I need 0.27, and for blue, means color, yeah, I need 0.23. So again, for the red, 0.5, for the green, 0.27, and for the blue, 0.23. If I go to mixture of these three colors, with the intensities 0.5, 0.27, 0.23, I get this color. Is it clear by the Sirskaitis?
Jā, ir.
So this is the idea how our cells are working when they accept different colors. So the complicated color is a mixture of the simplest colors, three simplest colors, single colors, red, blue, and green. And because of the different intensities of these colors, we can see different, actually, the entire range, the wide range of different colors. So this definitely is in use by the professional, I mean the painters, and one of the painters that actually provided the revolution in the painting art was Kazimir Malevich, and he developed the triptych, three figures painted with black color. The most famous is the black square, this one. And you can say, what is the art? Actually, from the first touch, nothing. Just to get the black dye and make a paint, nothing else. But so there are 2 points, I'm sorry. The first one, that this is a part of the composition. So this is like the decoration, and this composition may be accepted by different ways. But at the same time, actually, the black one now tried to switch the light at your rooms, and you see the magnification of this black picture, and you see that actually it isn't the clean black. This is a combination of different colors. And actually, this is the right art by this painter, by this artist, to get the black one from different colors, assembling different colors. He had achieved the black one. Is it clear? Vai tas ir skaidrs?
Jā, ir skaidrs.
Dzirdu?
Ir skaidrs.
So this is the distribution of the intensities in the comparable scales. So this is red, this is the green, and this is the blue. Have a look. The highest intensities that can be accepted or detected by our cells is the blue one. The blue color has the highest intensity, highest signal. So this means that the blue color load our vision system by the highest way. So the conclusion, the practical conclusion, is very simple. Don't paint your rooms with the blue color, because the eye system, the vision system, in this case, is loaded by the highest way. So take, for instance, the green one. You can take, for instance, the red, but the red isn't so comfortable from the mental point of view, mental point of the human. So now we go to speak about the resolution of our vision system. Resolution definitely depends on the cells, on the location of the cells. So this is a simple picture, a simplified picture. There are two cells, and there is some distance between these two cells, and definitely we are unable to provide resolution less than this distance. So for instance, we have the object at some distance from the eye, and the typical size of this object is d. This distance is d small, and the distance from the lens to to the cells is L small, and this is a L capital. So that is why the size D that may be detected or vision may be very easily to calculate it if we get D and multiply with ratio L to L. So this is from the simplest geometry. So now, if we know these distances L, and typically, so anatomically, this is 25 millimeter, and for the best reading, for instance, we need to have somewhere 220, 50 millimeter distance. So this means that the size of our object relates to the distance in between the cells with the proportional coefficient 10. So that is why, if we know this one, we can calculate what is our vision system resolution, D capital. So now we go to identify the distance between the cells. This we need to have the information about the distribution of the cells. So have a look at this diagram. This is the distribution, the density actually, of the rod cells, and the green line, the distribution of the cones over this surface, independence on the angle, on the azimuth angle. So, for instance, for the cones, this area where the highest or the majority of the cone cells are located is approximately 1 to 2 millimeter in diameter. So that is why, if we know the amount of the cone cells, roughly 5 millions, we can calculate how many cells per 1 millimeter of this area, not per diameter, but per area. And after that, to recalculate what is the distance in between the cones. Have a look. So the density of the cone cells is 5 million with the square of this area, PD square, pi d square, I'm sorry, to 4. So we have the distance, the density is roughly 4 million per square millimeter. So if you divide 1 with this distance, with this density, we have the density and the square root, if you get from this, we have that the distance in between the cells, the cone cells, is approximately 0.5 micrometers. Is this clear? Is the calculation clear to you?
Jā.
Hello?
Yes.
Jūs necirdat, lūdzu atbildiet.
Jā.
Here, yeah, okay. So by the same way, we're going to calculate the distance in between the rod cells. So this area that the majority of the rod cells are located is approximately 12.5 millimeters. And the rod cells amount is somewhere 100 millions. The density that y to this area is approximately 2.8, 0.3. I'm sorry. The density is approximately 0.3 million per square millimeter, or the distance in between the cells is approximately 2 micrometers. So finally, we can say that the distance between the rods is approximately 2 micrometers, and the distance between the cones is approximately 0.5 micrometers. So we have this result. What is the limitation factor? Actually, this one is a limitation because this one distance limits us the smallest visible size of the object. Because if we have this one, the cones, for instance, only, definitely this dimension, this size may be 4 times less. But we need the rods to see it. These cells are responsible for the colors, but for the vision, for instance, in the not good illumination condition, we are using these cells. So that is why this is a limitation factor. If so, D is approximately 20 micrometers. And typically real is the person, the human, is able to see, to identify approximately 20 micrometers, means 0.002 millimeters. The object, it is impossible, it is very difficult to see by eye very small objects, less than 20 micrometers. And now we assume that we are watching a TV screen, some monitor, for instance. And the distance we are sitting in the armchair, for instance, in the front of the TV, is approximately 1 meter. In this case, the coefficient instead of 10 is now 40, and the resolution that is available to us to see is approximately 80 micrometers. Actually, this is the resolution by the screen. This is the smallest dimension on the screen, the smallest dimension of the pixel that may be detected. And this is very important for the technology of the TV. So that is why when I am going to the market to buy the TV set, and somebody is telling to us that the pixel is very, very small, less, significantly less than 100, maybe 80 micrometers, for instance, 1 micrometer, you can ask, what for? I don't see it, because I don't see it closer than 1 meter. More longer is this distance, less resolution at the screen I need. Is this clear? The questions, please. No questions? Nav jautājumu?
Izskatās, ka nē.
So have a look at 2 pictures. Try to identify how much are they different. And if you see the difference, try to explain what is the difference between them. Can you tell me what is the difference? Hello? Hello? Please explain. Lūdzu atbildiet man. Allo, vai dzirdu jūs?
Tas varētu būt pikseļu blīvums, nu, vai ne?
Okay, so the version is the density of the pixels. Good. Can you motivate your feeling? How do
Tāpēc,
you
ka,
feel that the density of the pixels is different?
tāpēc, ka skaidrāka bilde ir viena.
Kas mainās?
Nu, skaidrība, es nezinu, izskatās viņa daudz tīrāka un, nu, ar vairāk detaļām, kuras var redzēt.
But so, if I'm speaking about the resolution, is the resolution different or not? How do you think?
Nu,
Just speaking about the geometrical resolution.
domāju, ka nē.
No. Okay, the geometrical resolution is very similar, but the colors are different. The right one picture has more saturated colors, and this is because of the higher amount of the pixels. So now we know what is the reason to buy, for instance, the TV camera the camcorder or the photo camera with a very high number of the pixels. So means this, the highest number or the higher number of the pixels means quality of the colors. Next, adaptation of the eye. For instance, the eye is located, we are sitting in the very dark conditions. And because of this, with time, we can recognize less and less photons, less and less intensity of light. Have a look. Somewhere, there are minutes, somewhere in 10 minutes, the cones are not able to see anything. So they need very high intensity. So next, the rod are switching and their intensity, the threshold intensity, somewhere 40, 50 minutes sitting in very dark conditions, still is enough to detect light. The cones doesn't work anymore, but the rods are able to detect light. But for this, we need to stay in a dark conditions approximately 40, 50 minutes. So this result was very well known by physicists at the beginning of the previous century. The physicist Rutherford, versus the Nobel Prize winner, he used these capacities of the eye to detect a very, very low intensity after sitting in a dark conditions to discover the nucleus of the atom. And now have a look. I believe that this is a very genius experiment that Rutherford didn't have so excellent equipment that we have today. He didn't have the accelerators. He had just own eye. So before Rutherford, the model of the atom was like this. So some gel, this is the atom, and the electrons are somewhere here, they are flying, can be moved. So this was the Thomson idea. However, Rutherford discovered it, but it isn't true. He said that there is some nucleus at the mid of the atoms and the electrons are around. So this conclusion was made just because of the very simple experiment. He had taken the positively charged alpha particles and directed to the atoms. And the particles changed the trajectory, changed the direction of flight, and became reflected back. So this meant that the positively charged particles interacted within the atom with something positively charged. And so this is the result of the Nobel Prize. The nucleus of the atom became discovered, and today we know this very well. And when we use this, particularly in medical physics, we use this result for radiation therapy. And now let's come to the Rutherford experiment. So this was a very thin gold foil, and this was the screen, the luminescence screen. So this was the alpha particle emitter or source. So Rutherford directed the beam of alpha particles to the gold foil. Within the gold, the particles interacted or collided with the atoms, and some of the particles became reflected back. Definitely, he expected that the particles will be scattered behind the foil. However, he was surprised when he watched the flashes on the screen. Again, very dark conditions, very long time sitting and watching on the screen. He really was surprised to see the flashes on the screen before the foil. So this meant that the particles became reflected back from some positive. Moreover, knowing this angle and knowing the mass of the particles, he was able to identify what is the mass of the nucleus. It was in order the same as the alpha particles. That is why he said, perhaps the positive charge of the atom is assembled or concentrated within the nucleus or by the nucleus. And now the model of the atom became very clear, because it was unclear why are only the electrons here? What is the positive charge? Because everything must be neutralized. And now, because of the Rutherford, we know that there is a positively charged nucleus because of his knowledge about this result, i.e. adaptation in dark conditions. So that is why when I'm speaking to young researchers, I'm telling them, before to buy very expensive equipment for your experiment, sit and think, how can you measure by the simplest and by the cheapest way? Question, please? Nav jautājumu?
Nav.
Labi. Tagad pārtraukums, jā, 5 minūtes. So we are back to continue.
Yep.
Yes.
So the other relaxation or adaptation of the eye is connected with excitation, with light excitation. So have a look. This is time, and this is the signal that was measured when the cell that the cell is excited by light. So dark, and now it is a light signal, light excitation. Have a look, the very high jump up, definitely the signal is very high. However, after some time, very, very short, approximately 0.4 seconds, the signal is going to relax. So this means that the cells have the adaptation to light excitation. I can't explain you what is the reason of this adaptation, but it is. So approximately 0.4 seconds or maybe 0.5 seconds, our cells need to be adapted to light excitation. So again, we have the light signal very bright, and the cells are going to be adapted to this signal. And after that, they are working, yeah. So now we are switching off the signal, again, a little bit of relaxation time and stabilization. So this means that the cells are not able to detect the light signal immediately. This is fast. They need some time. When the signal is switched off, they need again some time, have a look here, to come into the native initial position. Now, we're delivering light to the cells. And for instance, this cell is excited. But after some time, the signal is switched off because of the movement of the object. The signal is switched off. However, the cell isn't still ready to get the next signal because of this relaxation and because of this relaxation. So that is why we need to do something. We need to help the cell and to move this cell from the position where the light excitation comes and to locate the next cell at the same position. We can do this because of such vibrational motions. Is this clear? Vai tas ir skaidrs? Lūdzu jautājumu. Allo?
Jā, ir skaidrs.
How this can be done? What we have for this? This we go to the first slide of our first lecture about vision.
Blinking, maybe?
No. Have a look, for instance, this blinking, as you said, has a time interval several seconds. But we are speaking about the half of the second, maybe a little bit less. So the other ideas?
Zīlīšu saraušanās. Ja būtu kaut kāda
Vai tas notiek, vai tas notiek? So have a look. I have the muscle system. So these muscles that we have spoken at the beginning, and we said these muscles we need to rotate this sphere to follow the motion of our object, they are in use for these vibrations. So they have these vibrations and the frequency is 0.1 per second. I'm sorry, 0.1 second means 10 vibrations per second approximately. They have this frequency. So that is why, have a look, they have double function to follow the object and to provide these vibrations. Is this clear? Lūdzu, jautājumi?
Ir
Nav?
skaidrs. Nav jautājumu.
So this was the last slide, speaking about the vision system. So next time we have the test on vision. Please be prepared. So tad nākamreiz mums būs tests redzes sistēma.
Jūs pievienosiet tur papildināsiet to prezentāciju? Šobrīd tur ir tikai par to, ko mēs pagājušais runājām.
Nē, jau ir.
Nu, cik es redzu, tur ir pēdējais slaids par fokusu, ko mēs redzējām pagājušais.
Es pievienoju.
Varbūt pamēģina restartēt vēlreiz, tā kā pašu lapu.
Tātad citi redz? Citiem ir šie faili? Alo. Tas bija pievienots kaut kur 2 dienas atpakaļ. Kolēģi.
Man arī nav.
Es pārbaudīšu. Gadās, ka Ortus strādā ar kaut kādam aizkavēšanu, bet ar kaut kādam kļūdam. Labi, es pārbaudīšu, ja nav, es īstenībā jums pievienoju visus materiālus līdz galam. Tūlīt es pārbaudīšu.
Nu, tur ir pēdējais slaids par to Frenhoven difrakciju un tālāk nav.
Nē, bet jūs redzat, tātad 20. acis nav, jā, tur.
Tur ir tā prezentācija, bet viņa nav pilna līdz galam. Tur nav iekšā tas, ko jūs šodien stāstījāt.
Ok, labi, būs, jā, es saprotu. Es saprotu savu kļūdu, jā. Labi, būs. Jā, es domāju, ka tas tur ir jau. Ok, labi, nepārbaudīju, pardon, būs, šodien būs. Tā, labi, so now we're going to speak about the cell membrane. So the cell membrane. So this is a rather complicated design. You see, we have several membranes. So this is the external membrane that surrounds and actually is a boundary in between the extracellular matrix and the intracellular matrix. So there are some organelles inside that each of them also has a membranes. So if you go to have a look microscopically at the membrane, we see that membrane consists of 2 layers of some molecules. The molecules have a strange design, like the head and like the tails. This is one layer, and the other layer is below. We can see that these heads, like the balls, they are flotating because some very large molecules, the protein molecules, are very easily are able to be inserted in this layer. So we can find some molecules, protein molecules, have a look with some channels, and they are serving as a gates to propagate the ions from outside to the intracellular matrix of the cells. We can find the molecules without the channels, and these molecules are able to be moved in these cross-section directions. So, but first, have a look at this surface. The surface is rather regular, you see? It's rather regular, and so this is a model of the flotating balls from ping pong on water. We are just getting them on the water, and we see that they deliver the order by themselves. We don't help them. But we see really this is a rather well organized structure, you see? But the organized structure means that the structure has the crystalline properties. This means that this system, the cell membrane, is like the crystal. Actually, this is a crystal, but not the crystal that we understand as a solid crystal. This is a crystal that is named molecular crystal. And this is a model of the molecular crystal when the molecules are assembled together, but in the same direction. This is so-called nematic phase or nematic structure of the molecular crystal. And because these molecules are flotating, we are saying that this is a liquid crystal. So this is a nematic form, the nematic structure of the liquid crystal. There are different structures, some different. So this is a structure where the nematic structure, several nematic structures, deliver several layers to provide so-called smectic structure. So this is a smectical liquid crystal. Speaking about our membranes, we have nematic structure. So there is more complicated structure, so-called holosteric structure, when we have the nematic structure, again nematic, and they are located layer by layer, however, a little bit twisted. So this is the model of this layer. You see the molecule in one layer directed this way, the second layer this way, the second layer this way, and again, so they are twisting by the spiral. So again, the holistic structure. So some molecular structures are very well organized, and they are the crystalline structure. Have a look, for instance, tobacco virus. It's very well organized structure. Even the RNA molecule is also very well organized in one direction. This is a single directed molecular crystal. So the organic, the life world seems is also rather well organized, and it is a crystalline one. So let's come to consider the model of our membrane. So it is well organized in this direction too. So we can find such a system also organized one layer, single layers membranes, so-called micelle or micelle membrane. But typically the cell membrane has a double layer. We use these properties of the liquid crystals in technique. So this is a multi-layer system of our watch display. This is light. This one is a very thin glass plate that has a polarization property. The light may be polarized or is polarized by this plate, by this filter, into the vertical direction. So this means that electrical component, if we are speaking about the electrical component of light wave, the electrical component is directed in this direction, this one. So behind this filter, we don't have any other directions except of the vertical one. Next, the light is able to propagate through this multi-layer system. Now we'll follow the light. So this one is a transparent electrode that has, by some technology, has the digits, you see? So these digits means the electrodes. If you deliver the electrical potential, this light passes this potential. So just a second, somebody is calling from the university to me. I need to reply. Sorry. So sorry, the next one, the electrode of this one, is a liquid crystal coated that has so-called, the crystals, the molecules, has the directions like this one. So that is why we have the circle on this is so-called twisted nematic liquid crystal. So the next one, different, oops.
Jums mikrofons nometots, ja jūs runājat.
Tagad dzirdam?
Jā, tagad dzirdam.
Okay, paldies. So the next one is a transparent electrode. Next, we have the same filter as here, however, polarization in this direction. So this means that, for instance, if light is polarized in this direction, it is unable to pass this filter because this filter provides polarization in this direction. So, and the last one, this is a mirror. Now have a look what is happening. First, we deliver the electrical potential in between these digits and this electron. For instance, the potential is equal to 0. If so, this polarized light doesn't have any influence from this digit and passes this layer goes to this twisted filter or twisting filter and is polarized secularly. So this is the polarization of the light that was polarized linearly. So goes here. Now some part of this light is polarized in the horizontal direction and is reflected back. Comes here, again polarized, and again reaching this filter. Some part of this polarized reflected light again is polarized vertically. So that is why the light that be sent ahead reflected back with any changes. We see light. Now we provide the voltage. If it is a voltage, the electrical field here influence this polarization. And we try to keep by this voltage the polarization in this direction. This means no any more circulating polarization. This light polarized vertically reaches this filter, and behind the filter is unpolarized because it is impossible to pass this filter to this light. If to pass this light through this filter, if this light is polarized in this direction, yeah, it can. It's able to pass, but in this direction it is impossible to pass. So this means nothing can be reflected. Means nothing of light back. We don't see light exactly at the location of this electrode. Is this clear? Vai tas ir skaidrs, lūdzu, jautā.
Jā,
Ir
ir.
skaidrs.
Okay. So this means when we see our display of our watch and we see the digits, means nothing of light is reflected back. We see the dark digits. And so this idea came from the nature, from knowing of the molecular system polarization or knowing of the liquid crystal that came actually from our knowledge about the cell membrane. Now we go to speak about the processes that are able to transfer the molecules or ions through the membrane, because definitely the internal part of the cell, intracellular matrix of the cell, needs ions, water, proteins to provide the metabolic reactions within the cell, because metabolic reaction means our life. If we don't have metabolic reactions means we don't have life. So there are several mechanisms that we know today. Diffusion is the first one, maybe first because it's the simplest. So because of the diffusion, or to get the diffusion, the concentration of the molecules or ions mustn't be uniform. So for instance, this is the X direction and this is the concentration. We have to have the gradient of the molecular concentration. In this case, the molecules are able to be transferred in this direction to the higher concentration, to the lower concentration. It's well known, and this is a diffusion process. And the diffusion flow, J, is directly proportional to the diffusion coefficient and to the gradient of the concentration with minus. Because minus, we have spoken about this when we considered heat transfer. The same reason. The diffusion coefficient depends on temperature. This is some constant, it's named diffusion constant. This is a Boltzmann constant. This is the Kelvin temperature. And this is so-called activation energy. This is a parameter that characterizes how many energy is necessary to the molecular to be shifted at one step. To be shifted at one step. For instance, jumping from one position to the other one, what is the energy that we need for this shift? Now have a look. What can be happen if the temperature increases? So we increase this temperature, means this one decreases because of minus the exponent is increases, exponent increases. So in fact, the coefficient, the diffusion coefficient increases very, very strongly exponentially because this is the exponent. As a result, the flow increases also very strongly exponentially. Is this clear? Vai ir skaidrs, lūdzu, jautājumi. Halo?
Ir skaidrs.
Skaidrs, labi. If it is clear to you, can you tell me, we have the patient, it has a high temperature, for instance, 39, and we want to give some medicine to this guy. What we need to do the first, the version way A, to decrease the body temperature and to deliver the medicine, or to keep the high temperature and deliver the medicine. What is the most effective way for treatment? Jautājums ir skaidrs? Is the question clear? Why? High diffusion, why? Because of the formula. Because of the higher diffusion coefficient. And the higher diffusion coefficient is delivered by higher temperature. So this is a full explanation. Is this clear to everybody? So have a look. Temperature grows. This falls down. This is minus. Minus means 1 divided with exponent. Yes? If this falls down, the exponent falls down, 1 divided to the falling down exponent is rising. Is this clear? Okay. Have I explained you? Why? J, because the gradient is minus. The gradient is negative. I refer it to the heat transfer. The gradient is negative, so X is positive, but C falls down. You see, for the higher X, we have lower C. The gradient is negative. More questions? So the next transfer way or channel is Kinox. So this is some protein molecule that is located within the doubled layer. And because of some fluctuation, for instance, the heat fluctuation, the density somewhere here is changed, like this one, and the molecule has the ability for movement. However, behind the molecule, the density became higher again because of the fluctuation, and that is why we have such a motion, such a transfer. This is a Kinnock process. The next one, the electrical transfer. If you go to have a look at this molecular, so this is a lipid layer. So this is a molecular. This is a part of that we said the head. Have a look. The head is polarized, plus, minus. The tail isn't polarized. The head is polarized. That is why, because of this electrical polarization, the water molecule that comes to the surface of the membrane is influenced by this electrical polarization field. However, or alongside, this external part of the molecule, the head part, has a hydrophilic capacities, means likes water molecule. But this part doesn't like water molecule. This is a hydrophobic part. Now, what we have? The molecule is here somewhere, means the molecule is influenced by this electrical polarization field because of their molecular structure. If the molecule comes in, or because of some reason, maybe less concentration of water here, the molecule is able, due to the diffusion process, to come here, immediately this molecule is moved out of this hydrophobic layer because this layer doesn't like molecule of water. Very fast out. And again, somewhere here, this molecule is under the electrical polarization field. So this means that transfer of ions or dipoles, this is a dipole as you know, are influenced by the electrical field, are influenced, this means transfer depends on the electrical fields by the molecular structures. Independence of the structure, we have different influence. Have a look what we have here. We have the electrical potential difference here, and the molecular or ion transfers or passes these two electrical fields. So this is the reason that the electrical current, ion current, or dipole current, for instance, dipole flow, is influenced by properties of the membrane. So now we go to calculate the electrical current of ions through the membrane. So first, the simplest example. So for instance, this is some conductor. This is a cross section. There is a concentration of ions within this conductor. And this is the velocity of the ions. The flow of these ions, this one, is equal to the velocity of the single ion multiplied with the cross section and with the concentration of the ions. The electrical current, or the density of the current, it's more, right? We need to divide with this cross section, means per 1 square centimeter or millimeter or square meter. So the density of the current is just V with C, the velocity with the concentration. If you apply the electrical field, and if these particles are electrically charged, because of the electrical field, there is some force that acts on this particle, charged particle. So this is the force that acts on these particles. Now you see the U coefficient. This coefficient characterizes how effectively this force works. Means how the particle, or how strongly the particle is influenced by the force. And this coefficient U is named mobility. The force that acts on a single ion may be calculating if you know this Faraday formula. So this is the Z number of the ion, the atomic number. E is electrical charge, and this one is the gradient of the electrical potential of the field where this ion is moved. However, if you speak about the ensemble of the ions, for instance, 1 mole, we need to multiply this one with the Avogadro number. And so this is the force that acts on the single mole, or 1 mole, and in this case we have the Avogadro number again. So this E with Na is so-called Faraday number. So that is why we substitute this En with the F, Faraday number, and we have the force that acts on the entire mole at the located at the electrical field. So in this case, have a look. We write Fna here, and we have the velocity of the mole. So instead of Fna, we are writing this one, and we have the velocity of the entire mole. So that is why we have the electrical current that is delivered by the entire mole. This. Now, what do we see? If you increase the concentration of the ions, the electrical current increases too. If you increase the electrical field, this is a potential and this is X thickness, for instance, the electrical current increases too. So this is the idea, to get the ions of the drug into the human organism because of the external electrical field. We apply the electrical field and deliver the high concentration within the human organism, through the skin, for instance, because of the applied electrical field. Is the idea clear? This procedure is named electrophoresis. Is this clear to you? Lūdzu, jautājumiem, vai
Jā.
ir skaidrs? Lūdzu, atbildēt.
Ir skaidrs.
Okay. Now we go to consider more complicated situation if the diffusion and the electrical current, or electrophoresis, are working together. So this is the current, the flow from diffusion, and this is the electrical current because of the electrical field. We go to summarize them. J plus I, this one plus this one. If the total current is equal to 0, means this is equal to 0, we have such a result. You see, we have already that the diffusion coefficient is connected with the electrical field. But let's go ahead. The concentration, this is from the molecular statistics. The concentration C may be calculated as the initial native concentration with the exponent of the activation energy kT, the same that we had before. The electrical field is EF. E is a charge. If it is an ion, the charged ion, the E value is a positive. Therefore, instead of this activation energy, actually this is the electrical field that we apply to move the particles. We can very surely write E phi. Now, we go for differentiation of this one, dc dx. For dc dx, we have to rewrite this exponent, this constant, it is here, plus we need to get the differentiation of this one. It is minus ekt with d phi dx. I believe that you know how the exponential function may be differentiated. So, this one is here. It is C. So that is why this result may be rewritten again. This is this one with C, with this one. And this must be equal to this one. So d dc dx. D, this is a dc dx. This is dx with the same that we had before. So finally, I have the formula that have a look exactly the coefficient D, diffusion coefficient, is connected with the mobility of the ions. So seems for the electrical transfer that works together with diffusion, we have the interaction in between the mobility of ion and its diffusion. The question, please.
Nav jautājumu.
Tiešām nav. Es domāju, ka bija grūti, ja jums nav jautājumu. So what about the exam? Have you sent me already and you'll send me a little bit later?
Pirmais kurs jau ir atsūtījis.
Okay, labi. Paldies, jā, paldies. Jā, es vēl neskatījos, labi. So please, the other courses, the other groups, please send me your offers for the exam. Okay, so see you next time. And the next time again, we have the test on vision. So thank you for today and sorry for the technical problems. So see you next time. Goodbye.
Goodbye.
Visu labu.
Visu labu. Visu labu.
So I prefer before the 12th of June. No, 11th. I said before. Welcome.